this screencast, we're going to take a look at specifically metathesis reactions, which are also called double displacement, and in some specific cases, precipitation reactions. The picture that's shown here shows two beakers, and what we're taking two solutions here and mixing them together to make a precipitate. This yellow cloudiness right here in the beaker is commonly referred to as a precipitate. Metathesis means to transpose, and what that actually means, for example, in one of these beakers is a solution of lead 2 nitrate, and it's being added to a solution of potassium iodide. In this case, double displacement, ionic compound plus another ionic compound, and we're going to get the lead cation going now with the iodide anion to make lead 2 iodide, and potassium nitrate, KNO3. So we need two of those to balance the equation. We need 2 potassium iodides. Now, if you need help with balancing equations and predicting products of double displacements, let me know. But anytime we take a ionic compound plus another ionic compound and we get a precipitate, this is the type of reaction we're dealing with. We have to identify which one of the two products is the precipitate. Group 1 cations and nitrates are soluble, so that means the lead 2 iodide is our precipitate. That is our yellow cloudiness that's being formed by the mixing of these two solutions. So when we talk about representing reactions, normally in advanced placement chemistry, we're interested in the net ionic equation, which is just the formation of the precipitate or the liquid or the solid. Specifically, it's anything that changes during a chemical process. So in the example we had lead 2 nitrate plus 2 potassium iodides. We'll make lead 2 iodide, there's our precipitate, and 2 potassium nitrates. Normally what we'd do is anything that's soluble in solution we would split apart to get the complete ionic equation. So the lead 2 ion plus 2 nitrates plus 2 potassiums plus 2 iodides will produce our lead 2 iodide, PbI2, plus 2 potassiums and 2 nitrates. Now, the other thing that we can do with this, that's called a complete ionic equation. It represents all the ions that are present in solution, but you'll notice, for example, that the 2 nitrates don't change formula on either side of this reaction equation, neither do the 2 potassiums. Those are referred to as spectators. So to get the net ionic, we'd eliminate the spectators, and we would have lead 2 plus 2 iodides produces lead 2 iodide, and that would be the net ionic equation. So some of the things you need to keep in mind while doing this is the only thing that's soluble in water that gets split apart into its ions or completely ionizes is your strong acids or bases and your soluble salts. That stuff gets split into its ions. So that means, for example, if you took a solution of hydrochloric acid, HCl, and added it to sodium hydroxide, this would be called a neutralization reaction, an acid plus a base. We would end up making hydrogen hydroxide, also known as water, that's in its liquid form, and we'd make sodium chloride, which is a soluble salt. Since hydrochloric acid is a strong acid, we would actually ionize it into hydrogen cation and chloride anion, and we would add it to sodium cation, because sodium hydroxide is a strong base, and hydroxide anion, and that's going to produce our water. Since it's a liquid, we leave that formula alone, and the soluble salt, sodium chloride. And you'll notice in this example here that the sodiums and the chlorides are spectator ions, and we're left with hydrogen plus hydroxide making water. Hope this helps a little bit with writing net ionic equations. We're going to practice it plenty in class, so if you need additional help, feel free to let me know at any time.